Today, we will talk about the concepts of pressure altitude and density altitude, which are concepts widely used in aviation, especially in aircraft performance calculations. And if they are not well understood, can be quite confusing. So, without further ado, let's start with the pressure altitude. It is abbreviated as PA and corresponds to the altitude of the aircraft in relation to the standard isobar of 2992 inches of mercury or 1013 hectopascals, which, as we recall from previous videos, corresponds to the pressure at sea level under standard conditions. Therefore, we can also say that this pressure altitude is the altitude indicated by an altimeter adjusted with the QNE, since in this case, the altimeter would be measuring the altitude in relation to the standard isobar. And considering that in the ISA model, the pressure at each level has a fixed value, we can also say that the pressure altitude is the altitude in the ISA atmosphere where a certain pressure is found. Another thing to keep in mind is that the definition of pressure altitude is exactly the same as the definition of flight level. Therefore, the pressure altitude will always be equal to the corresponding flight level. Let's look at some examples of how this pressure altitude varies depending on the present conditions. Let's begin with the standard conditions. In this case, the sea level pressure is 2992 inches of mercury. Therefore, as the QNH and QNE are equal, we can say that the pressure altitude is equal to the actual altitude. Now, this only happens if the conditions are standard. Since if we have, for example, a higher than standard pressure conditions, the QNH will be higher than the QNE, which means that the 2992 isobar would be above the sea level. Therefore, in this case, the pressure altitude will be lower than the actual altitude. On the other hand, if there are lower than standard pressure conditions, the QNH will be lower than the QNE, which means that the 2992 isobar would be below the sea level. Therefore, the pressure altitude will be higher than the actual altitude, as we can see in this example. Having understood the concept of pressure altitude, let's see how it is calculated. There are several methods to do it. We can use either a table with correction values depending on the QNH, or directly use the altimeter of the aircraft, or use an approximate formula to determine the pressure altitude. Here are some examples of how to use each of these methods to determine pressure altitude. Let's begin with the table. Suppose we have the following conditions: a QNH of 3020 and an indicated altitude of 12,000 feet. Here, if we look at the table, we can see the different correction values to be applied depending on the QNH. In this case, for 3020 the correction value is -257. Therefore, all we have to do is take 12,000 feet and subtract 257 feet, obtaining a pressure altitude of 11,743 feet. Now, let's see how to determine the pressure altitude using the altimeter of the aircraft, using the same conditions as in the previous example. So, normally our altimeter will be adjusted with the local QNH of 3020, in this case indicating an altitude of 12,000 feet. To determine the pressure altitude, all we have to do is adjust 2992 in the altimeter and read the altitude indication. In this case 11,740 feet. Finally, let's see how to use the approximate formula using the same conditions. Here, we just have to replace the indicated altitude and the QNH in the formula and do the math. Obtaining a pressure altitude of 11,720 feet. It is important to mention that this formula is applicable only when using inches of mercury. If the QNH is expressed in hectopascals, we can use this other modified formula. Having seen what is the pressure altitude and how to calculate it, let's continue with the concept of density altitude, which is abbreviated as dA. It is defined as an altitude in the ISA atmosphere where a given density is found. It is a fairly short definition, however, sometimes it can be difficult to understand. So we will try to explain it in an easy and simple way through the following examples. First of all, we must part from the idea that in the Earth's atmosphere, the air density decreases with altitude due to the pressure reduction. This means that at low altitudes, the air molecules are closer together, which implies a higher air density. While at higher altitudes they are further apart, which implies a lower air density. It is important to note that air density is a determining factor in aircraft performance, since the thrust produced by the engines, the lift produced by the wings, among other things, depend on air density. Therefore, it is very important to understand the concept of density altitude. Now, as we can see in the definition of density altitude, the ISA atmosphere is mentioned, since this is the main frame of reference to be used. Here we have then an air column with standard conditions. This means that at sea level we have a pressure of 2992 inches of mercury and a temperature of 15 degrees Celsius. And as we saw in the video about the ISA atmosphere, pressure decreases at a rate of 1 inch per 1,000 feet, while temperature decreases at a rate of 2 degrees Celsius per 1,000 feet. Therefore, at 1,000 feet we would have a pressure of 2892 and a temperature of 13 degrees. At 2,000 we would have 2792 and 11 degrees, and so on. Now, let us remember that air density depends mainly on pressure and temperature, although it also depends on humidity, but we will not take this into account. So, considering that in the ISA atmosphere the pressure and temperature at a certain altitude are always the same, this means that the density at a certain altitude will also be always the same. To illustrate this, let's assign a certain density value to each altitude in the ISA atmosphere, depending on the pressure and temperature at that altitude. We must clarify that these will be fictitious density values, which do not obey to any unit of measurement, since they will only be assigned for the purposes of the example. So, suppose that the combination of 2992 inches and 15 degrees results in a density of 12. Again, this is a fictitious value. Then, let's say that at 1,000 feet, the combination of 2892 and 13 degrees results in a density of 10. Then at 2,000 feet, a density of 8. At 3,000 a density of 6. And at 4,000 a density of 4. With this in mind, let's say we are at an airport with an elevation of 2,000 feet and the conditions are standard. Well, as we can see in the ISA model, at 2,000 feet we find an air density of 8. Therefore we say that the density altitude is 2,000 feet. Nothing complicated so far. We can then say that in standard conditions, the density altitude will be equal to the actual altitude. Now let's see what happens if the conditions at the airport change and we now have a higher than standard temperature and a lower than standard pressure. Well, the combination of these two factors will cause the air density to be reduced. Let's say, for example, that this combination of factors results in a density of 6. If we then look for this density value in the ISA model, we can see that we find it at 3,000 feet. Therefore we say that under these conditions, the airport has a density altitude of 3,000 feet. Although the actual elevation is 2,000 feet. This implies that the aircraft performance will behave as if the aircraft were flying at 3,000 feet, even though the actual elevation is 2,000 feet. Simply due to the fact that the conditions cause the air density to be lower. Now, the opposite happens when we have higher than standard pressure and lower than standard temperature conditions. In this case, the combination of these factors will cause the air density to increase. Suppose, for example, that the combination of these factors results in a density of 10. If we then look for this density value in the ISA model, we will find it at 1,000 feet. Therefore, we say that this airport under these conditions has a density altitude of 1,000 feet, although its actual elevation is 2,000 feet. This means that the performance of an aircraft will behave as if it were flying at 1,000 feet due to the increased air density. In conclusion, if the density altitude is low, it means that the air density is high. And if the density altitude is high, it means that the air density is low. For example, a density altitude of 1,000 feet will represent a higher density than a density altitude of 8,000 feet. Let's finish this explanation with the next example. Suppose that the airport A with an elevation of 3,000 feet, reports a QNH of 38 inches of mercury and a temperature of 0 degrees Celsius. This indicates a relatively high pressure and low temperature, which will cause the air density to be high. Now, since the air density is high, it means the density altitude will be low. In this particular case, it is 1,670 feet. In other words, aircrafts operating at this airport will behave as if they were flying at 1,670 feet, which means that they will present a good performance. On the other hand, let's look at Airport B, which also has an elevation of 3,000 feet, however it reports a QNH of 2980 inches of mercury and a temperature of 30 degrees Celsius. This represents a relatively low pressure and high temperature, which results in a low air density. Now, since the density is low, it means that the density altitude will be high. In this particular case, it is 5,600 feet. In other words, aircraft operating at this airport will behave as if they were flying at 5,600 feet, which means that they will present a poor performance due to the reduced air density. Now, having understood the concept of density altitude, let's see how to calculate it. There are several methods to do it. We can use a flight computer, either manual or electronic. We can also use a graph or table like this. Or we can use an approximate formula. It is important to mention that in some airports, the ITAs calculate and broadcast the density altitude based on the current conditions. That way, the pilot doesn't need to calculate it manually. With this being said, let's see some examples of how to determine the density altitude using each of these methods. Let's begin with the flight computer. For this, we will use the inner scales, specifically the little scale in the center and the upper right scale. In order to calculate the density altitude, we have to know in advance the air temperature and the pressure altitude. The first step is to align the pressure altitude with the corresponding air temperature in the upper right scale. Then we just have to read the resulting density altitude in the center scale. Let's look at a practical example. Suppose we have to determine the density altitude if the pressure altitude is 5,000 feet and the air temperature is -10 degrees. First, we have to align 5,000 feet with -10 degrees in the upper right scale, as we can see here. Once this is done, we read 3.1 in the center scale, which corresponds to a density altitude of 3,100 feet. Let's now move on to the approximate formula. To use it, it is required to know in advance the pressure altitude, the current air temperature, and the standard temperature at that altitude. This means that here we have an additional step, since we have to determine the standard temperature at the corresponding pressure altitude, which, as we will remember from previous videos, can be done by means of this other formula. Let's see a practical example. Suppose we have the same conditions as in the previous example. The first step then is to calculate the standard temperature at 5,000 feet. So we apply the corresponding formula, obtaining a temperature of 5 degrees Celsius. Once we have this information, we can now replace the values in the density altitude formula, obtaining as a result a density altitude of 3,200 feet. Finally, let's see this example using the graph. Here, the first step is to identify the line that represents 5,000 feet of pressure altitude, which is this one highlighted in yellow. Then, in the lower part, we look for the current air temperature, which is -10 degrees. And we draw a vertical line until intercepting the 5,000 feet line. Finally, we just have to draw a horizontal line to the left and read the resulting density altitude, which in this case is 3,150 feet approximately. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe and leave a comment down below. Thanks for watching.